Thank you. Yeah, we should also mention, Viral Shah, who started the project with us as well, and Alan Edelman, who's sort of been our patron from the beginning. But yeah, we're no longer at MIT. We started a company called Julia Computing to do training and support for the language, but that is not why you're here. You're here to hear us talk about numerical applications pushing the limits of programming language design. So I think we are holding up the sort of numerical end of most of this 2 days of talks. So here's some, if you haven't used or heard of Julia, here are some features that might be meaningful to you. First of all, in the context of Gilad's talk this morning, it's a dynamic language. People who do a lot of work with numbers and data and figuring out algorithms to make sense of those numbers and data, they really like these interactive exploratory environments. And this is very much about the exact same kind of liveness that he was arguing for. And we feel the same way. So we had really in our minds, no other choice but to make it a dynamic language. In order to get performance, we knew we were going to have to do just-in-time compilation. The technology for this is great these days. Usually just-in-time compilation is applied to dynamic languages that already exist as a sort of, an add-on to try to make them fast after the fact. We planned for it from the very beginning, and there's a lot of ways you can design a language to make that easier to take advantage of. And in fact, I think I was having dinner with Carl Boltz, who is one of the PyPy guys one time, and he described Julia's just-in-time compilation as ahead-of-time compilation at runtime. And I was very confused because I was like, isn't that what just-in-time compilation is? And then I realized what he meant is that usually that comes with this whole other bag of tricks you do, like guessing what the types of things are based on traces, and then optimistically generating code that does that fast but does some checks, and then bailing out if you turn out to be wrong. We don't actually do any of that. We have a fairly stupid just-in-time, ahead-of-time compiler. The cleverness is in actually being able to express and figure out what the types are. To that end, we do have a fairly powerful language of talking about types in the language. And it turns out that multiple dispatch is a really powerful paradigm for numerical computing in particular. The most obvious, case is you say C A plus B, and what code gets invoked there doesn't really just depend on the type of A. It depends on the type of B as well. And there's some awkwardness. Other languages will let you overload this, like Python has this radd stuff, but it feels like a bit of a hack. But it does work. So one of the things we had is sort of like early design of the language actually could very much be summed up as what does it take to make plus just a function. And plus is a very, very, even in completely monomorphic languages like C, you can even write 1 plus 1 plus 5, 1.5. Like an integer and a float will work, a float and a float will work. So plus can do things that normal functions can't do. So these are sort of the early basic design things. What's come along over time, although Lisp-style metaprogramming and macros was actually there pretty early, but other things that have come along are carefully designed equality ordering and hashing, which I'm going to talk about next because it actually shows off a lot of other features of the language, and it's interesting in and of itself and not something you often hear about in languages talks. Metaprogramming and macros, and then a very recent feature it's in the development version, but not in the stable version currently. Easy to use implicitly invoked generated functions. And this is a form of staged programming that I put it in quotes because we actually had to coin a term for what exactly we're doing because we haven't seen it anywhere else. So if anybody has a good name for it that's better than generated functions, please let us know after the talk. So these last 3 points are what we're going to focus on here because we've given lots of talks about the other points in the system. Multiple dispatch is really a great paradigm, and I am so pleased with how that's worked out. So just totally different language, first of all, to introduce equality as an issue. What does this C program print? Does anybody want to guess? All right, so I happen to have this C program handy. You can see it here. Okay. So just to say that there's no tricks up my sleeve. That is the program. I'm going to compile it, and then I'm going to do run non-transitive. And so you can see it prints 1, 1, 0. Okay, so what's the big deal about that? Why is that a problem? Well, it means that equality is not transitive in C. Right? So if it was if the first two are true, that means they're equal. And the third comparison is comparing the first two, the last thing in the first thing in the chain, the last thing in the chain, then you don't have transitivity of equality. Now in C, this isn't such a big deal because you might argue that, well, those are really, it's just like you get to have syntax for different equality functions and they're not really related. And one of them is the float equality and one of them is the long equality, and they're not actually the same thing. So keep that in mind when we talk about the rest of this stuff. That's one issue. So we, for example, do things like this. I'll just show it to you. This works correctly in Julia, as you would expect it to. So let's say x equals 1e16, y equals int of 1e16. So you print out the whole thing. Z equals x plus 1, and x equals y is true. Y equals z is true. Wait, did I do something wrong here? X equals y. So let's see what x, y, and z are. Hold on, I confused myself already. Yeah, sorry. Z equals x plus 1. That's the. Yeah, that's y. Okay, sorry. Did I do? Oh, yeah, it's the first and the last ones are long. Sorry, I'm a little confused here. All right. X equals 10 to the 16th. Y equals the float 64 of the x. And then z equals x plus 1. And then x equals y is true. Y equals z is false. This is actually the key difference. All right, and then we expect that x and z not being equal is true, that they're not equal. So the key thing here is that you want that y equals z inequality to be an inequality, and the question is, how do you do that, and what's the point? Well, it's instead of just doing the naive thing where you just convert both to double and then do the comparison, which is what gives you true, and that's what C does. We actually have to make sure that we're doing the correct thing here, and we note that that is actually not an integer that is representable precisely as a float. And so the principle here, was like a very early thing that we were like, oh yeah, that's actually kind of broken. How can we actually do that comparison correctly? And actually you can see the LLVM code. If anybody's familiar with LLVM, that's good. You don't actually need to be. So what this does is it actually compares casts your floating point to an integer and then does a floating point compare, and then it casts your integer to a float and then does an integer compare and then ands those two. And so that trick gives you the correct answer all of the time, and you can prove that. Inequality is much, much harder. You might worry about certain things like, okay, what happens if I have a function that just checks if something is 0? So this is the notation for defining a function. There's a one-line definition, and then there's a longer thing that looks kind of like MATLAB or Ruby or something. You might want to say x equals 0. Okay, we check that it actually works. Is 0, 0? Okay, that's true. 0.0, okay. 1.0. And you'll note that I'm passing values of different types in here. So, and I haven't mentioned any types. But what's actually going on here, we can find out pretty easily by looking at the code LLVM again. All right. So what happens here is that even though there were actually those, so this is under the hood by the function definition, this is comparing a float and an integer. But the compilation process is clever enough to figure out that it's a constant float and actually propagate all of that through and then realize that, okay, all we need to do is do the floating point compare. So most of the time you actually don't have to do all of that nasty stuff. You get the performance you want. And of course, if you're comparing two floats, then there's no issue. You just use the floating point compare. Okay. So let's back to the presentation. There we go. Okay, so this that was, you know, sort of an early thing that we had to worry about and think about. Later on, we encountered an actually much hairier thing but that is also related to inequality and equality and hashing. So suppose D is a dictionary. This is, you know, valid syntax in a lot of dynamic programming languages. And you insert with the key 1, say, you know, D of 1 is equal to the string curry on. And then the question is, what do these dict lookups do? D of 1.0, D of 1 plus 0 imaginary, which is, you know, Julia syntax for a complex number. D of 2 over 2, that's Julia syntax for a rational number. So what are these going to do? They're all like mathematically equal to 1, but are we going to return that value or not? Because they're not exactly the same object. And so you know, in asking this question, you might look at what other programming languages do. And there's, you know, whole empires that have built on top of hash tables and dictionaries. So there's languages that really should have thought about this a lot. So here we create a dictionary in Ruby. We assign D of 1 to curry on. And then we check of D of 1.0. And we see that it, in fact, is nil, and that those things don't hash the same. But yet, 1 and 1.0 are equal. So that's a little weird. Okay, so I actually looked at what Python does. I was going to skip the slide, but since it seems fair to show it. Python actually does this right. They get good stuff. Oh, somehow it got cut off. I'm not sure what happened there. Yeah, so Python gets this right. D of 1 is equal to curry on, gives you D of 1.0 equal to curry on, and you can do the same thing with a complex number, which is in the standard library, and it also gets that right. I think where this falls down, Python does pretty well, is that if you then create your own numeric type, something that's supposed to be like a number, it's super awkward, and then you like have to, you can implement the hashing correctly by hand, but you know, it's tough to do. So Julia also gets this right, but as Python shows, this is entirely possible. So the question is, how do we do this? And how did we manage to do it without sacrificing performance? So we actually took a different approach initially, because this is a sort of stupid, obvious thing to do. In the 0.2 version, we actually hash numbers with different types differently. So those things, we did what Ruby does, which I think is actually defensible. It's totally fine to punt on this and be like, look, we don't really care that much. And so this would end up in a different slot, and you would end up with a dictionary with an entry for 1 and an entry for 1.0, and they're different. So that seemed good. It seemed really easy. It's certainly fast. It's simple to implement. Different types just are unrelated, and they don't have to worry about what the other types do. But then we encountered some weird stuff that made us unhappy. So we have this language of types, and we actually have parametric types. So for example, the dictionary type has 2 type parameters, which are, in this case, I'm saying that's the key type and the value type. And we can generate much more efficient code and much more efficient storage based on that if we know it. So this is constructing a dict with specialized, you know, key and value types, int and string. And so now, you know, you assign into it with, you know, D of 1 equals curry on. That's good, okay. Now what happens with the second thing, D of 1.0 equals ecoup? So there's 2 options. It's like not very clear what you should do here. So the 2 options are throw an error, which is not very dynamic or convenient, because I'm like, well, you know, I used a floating point number, or maybe I used an int 32 instead of an int 64, an unsigned int. But you know what I mean. It's 1. Like, we know how to convert between these things. We know what type you want, so why wouldn't we just do it for you? And so that's the other alternative, automatically convert to 1.0 to an int. So now this is a problem. The same key code would now work very differently depending on the type. So if you have an untyped dictionary, you end up with a dictionary with 2 entries. If you have a typed dictionary, suddenly you do the exact same thing, no errors are thrown, and you end up with a dictionary with 1 entry. This is bad. This is not fun for writing programs generically that work and do what you expect them to do. So we ended up coming up with the solution is to just bite the bullet and figure out how to hash numbers correctly by value. But of course, you know, the two elephants in the room at that point are, can you do it efficiently and can you do it generically? And And so I came up with a clever trick to do it efficiently at some point, which was actually based on exactly the thing we did with equality, right? The thing we did with equality was we converted to both int and float and then did the comparison. So I was like, oh, wait, what if we convert to both int and float and then do the hashing? Right? You can totally do that. So this is the solution. You define hashing. So here we actually see another feature of Julia, which is the multiple dispatch. You take a function, based on the argument type, you can define different methods, and then the correct one will get called. And the compiler knows all about this, so it can inline everything very efficiently and generate like good code for you. So for x being a float, when we hash it, h is just some function for hashing 64 bits of whatever. You can define it how we use murmur hash. You can use whatever you want. So you do some mixing function. In this case, it's 3a plus b, because that actually is fast to compute and avoids certain unfortunate collisions and cancellations. But that's sort of neither here nor there. So you hash x, and then you also hash the truncation of x to an int64. And then going on the other side, you go in the other direction. So if you have an int64, you convert it to a float, which can be done losslessly, and then you hash that and you combine the two. And so now those two hash values are going to be the same as long as those two values actually are numerically the same. And this is like slightly slower, but reasonably fast. But then what do you do about other numeric types? Like that's a cute trick for those two things. And you can actually make this work for unsigned int64s as well without too much collision. So this is sort of where Julia ends up having this large focus on these generic functions that you plug in certain methods to plug into them from below, and then anybody who uses that generic function in a generic way gets the same behavior. And you just have to sort of plug in the appropriate generic functions from below, and we'll see that in a second. So the idea is this decompose function, which again is not terribly well named, but I couldn't come up with anything better when I was working on this. So the decompose function is the point where if you have a rational numeric type, and you want to hook it into the hashing protocol. So like this actually happens. People write their own numeric types using Julia all the time. Like fixed point number types, polynomial types might want to hook into this, you name it, big ints, big floats. So the decompose function of x should return three integer values, the numerator, the power, and the denominator, such that the value of x is mathematically equal to the number times 2 to the power over the denominator. And that's like floating point numbers are sort of fall into this representation. Rational numbers fall into this representation pretty obviously, and so do integers. So you can compute those things very easily for all of those things. And then you have a fast special case where you do the trick from the previous slide if you happen to have something that's equal to these values. And let me just show you briefly what that looks like. We're not going to get into the nitty-gritty of it, but yeah, here. Okay. So it's the generic hash function, and this will work for any real type. You can overload it with more efficient, clever things as long as they match the semantics of this, and we do that for a bunch of things that you want to hash faster. But they're just faster ways to compute the exact same thing. So you do the decomposition, you handle nans and infs especially, you do some normalization. Then you check, and this is relatively easy to check in all of these, like finding the trailing zeros, finding the number of digits. These are all fast and easy to do on simple numeric types. And then you call out to the specialized versions that we already defined elsewhere. And then you get to the end, and basically you say, okay, well, if I have these three things and I've gone through all of this normalization and special type checking, all I need to do is call this like thing that efficiently hashes integer values and chain the hashes together and then return something. So you create a new numeric type. All you need to be able to do is say, okay, I can know how to represent it in this special rational form, and then I can hand it off and we're good. And so if you want to hook into this, you can do it relatively easily without actually having to know very much about this. All right. So I think that's enough about hashing inequality. So now I'm going to hand it over to Jeff, and he's going to talk about stage programming.
All right, thanks. So another problem we've encountered is that in the scientific computing space, program generation is unusually common. So basically programs that write programs. It's used very often. So, I mean, well-known examples, you might have heard of packages like Spiral or FFTW, which are basically programs that generate signal processing code, and it runs really, really fast. And so there are actually lots and lots of libraries like this in the numerical and scientific world. Basically, people can figure out tricks and how to generate really fast code for certain problems that a compiler is, arguably never going to figure out. Right? Sometimes you have to prove novel theorems to get these things to work. So you can't just expect a compiler to do it. So people write programs to write the programs, right? And this is a pretty difficult thing to do. This is kind of a black art. It's much harder to do that than just to write out the program yourself. So this was another thing that we wanted to try to address. What can we do about this? Can we make it easier somehow? So we've been trying to chip away at that as well. So stage programming generally letting you generate the code. So there's several forms of it one can contemplate. So here's a basic program translation pipeline starting with source text, ending up at native code. And there are various points where you could sort of hook into this and imagine doing code generation. So a famous one is macros, right, from the Lisp world, where you can basically intercept some piece of the program text or syntax tree, manipulate it in some way and change it and transform it. Or also, in a compiler backend, when a compiler does optimizations, and eventually generates code, it's arguably doing, it's another form of code generation. So you might try to hook in there and do something. But then there are other stages in between. So in particular, in Julia, we do some type inference, and we have some kind of a type system. So there's this other intermediate stage where one can imagine hooking in, where we have basically some information about the program, but not the runtime values yet. But we know more than just the basic syntax, and so we can actually hook in all of these stages to try to do these things. So some simple examples. So we started out from the beginning. We had macros. I like Lisp, so I like these tricks. So this is an example of a simple Julia AST level macro that basically generates efficient code for evaluating polynomials. And basically, you write out. You put in the argument, which could be some variable, and you put in the coefficients, and this will just loop over generating nested expressions to compute this. So I can just show what this looks like.
Do you want me to drive?
Sure.
Okay. All right. Okay.
So this is what a call to the macro looks like. We put an @ sign in front. That's our syntax for invoking this, so you know something special is happening. All right, so there's a function that uses it. We can see it evaluates polynomials. I guess that's the right answer. But you can see the LLVM code that eventually gets generated is just a straight line sequence of adds and multiplies. This is pretty much the optimal efficient code you can get for this.
Do you want to show the eval poly one?
No, it's okay. All right, so this for a simple case like this works fairly well, but this is actually pretty limited. So this is quite limited. You with something like that, you're basically limited to you have to know that you want a polynomial. You have to know how many coefficients. It's fairly rigid, and the basic problem with macros is they don't know that much about your program. They basically just know what it looks like. You look at the AST and if you think about it, there are many ways to program something. You can, to get the exact same result, you can type it differently, right? I could write A plus B or B plus A, and it does the same thing. You know it does the same thing, but a macro has this sort of excessive flexibility that if it wanted to, it could look at that difference and generate different code based on that. So a macro kind of doesn't obey the meaning of the program in some sense. It can just manipulate it in any way it feels like, which is kind of not so great. And it also doesn't have that much information. All it sees is the basic structure. The macro itself doesn't know what A is, what B is. It might not know what plus is either. It just knows that it's a plus symbol. So it's a little bit limited. And then a macro itself also doesn't work like a function. We like to just have functions. It's one of our favorite abstractions, I think. Probably all of us, I would hope. You can pass it to other functions. You can do all these things with it that you can't really do with a macro. You can't. They're not really very first class in some sense. So there are lots of problems with this kind of code generation. It's not so great. So we actually have a different mechanism that we developed. So let's see. So Julia is multiple dispatch. The basic paradigm is you define lots of methods for functions, and they're dispatched on all the arguments. So what this means is if you look at all the types of all the arguments, you actually have a fair amount of information. And so what we added a feature that lets you basically intercept at the point where the types of the arguments are known, whenever that might be, and generate code for those types. And so you've got an example of where we use that.
So this was actually very much a motivating problem for us. And I'm going to walk you through a little bit of why. So the problem we have is that our arrays are n-dimensional. So let me maybe just give you some examples of throwing around arrays. So you can have an array that is, you just generate 4 random elements. And we print it as a column because in math, vectors are columns. And this is, you can see the element types there is float 64 of the array. We also have type parameters that can just be values. So 1 can just be a type parameter. And in this case, it indicates that there's only 1 dimension to this array. But you can do things like, make a 2-dimensional array. So you have a matrix, 4x5 matrix. And you can see that the second type parameter for the array changed, indicating that we have a matrix. But of course, there are people who do things that are much bigger. This is not unheard of. It's actually pretty standard to do things in 6 dimensions for, doing, for example, if you have a field of velocities, right? There's, 3 dimensions of points, so your array is 3-dimensional, but then the velocities themselves are 3-dimensional, you got 6 dimensions. If you also wanted to track acceleration, you would have 9 dimensions. And so, you get fairly high dimensional things, and there's actually no real predicting exactly how many dimensions people are going to want to work with. We've seen some fairly crazy stuff where people wanted large numbers of dimensions. So let's just consider the problem of just trying to efficiently iterate through all the elements of an array. And so I have a diagram of an array. We'll see it in a second. Okay. So this is how you store a dense array in memory. And Julia is column major, which is, in the Fortran and MATLAB tradition. So you would actually iterate this efficiently in memory, going down the first column, then the second column, then the third column, the fourth, so on, so on, so on. And those are just at successive indices in memory. So there's this thing called linear indexing, which is done in MATLAB, where you can, even though the thing is 2-dimensional, you can just index it with 1 dimension. And what it does is it's like, okay, I'm going to ignore the fact that there are multiple dimensions here, and just offset from the beginning at that index and give you the element that's there. So you can scan through all of the elements in this contiguous array just by hopping through memory one step at a time. But then there's the thing that you frequently want to do, which is you want to slice a part of the array out. So you can, for example, the syntax for this is that you write you would write this particular slice as A:, 3:8, indicating that you want to take all of the rows and you want to take columns 3 through 8. Now in this case, we got lucky, and that is actually still contiguous, right? It's still contiguous. The stride, which is the step that you can go through, is still 1. So we can still use linear indexing to efficiently iterate through this. But now, let's say we just left off the bottom row. Now we can't do that anymore, because now all of this, we would at some point we need to know that we've reached a multiple of 4, and we need to loop back around, and we actually need to add an extra element. So now, there's various tricks you can do. You can do mods and divs and various other things to do this. In this case, doing mod 4 is not terribly expensive, but it could be mod 5, it could be mod 7, it could be mod anything. So you won't always be able to just do bit shifts and masks to do it. You can also have much more complicated patterns. You could easily have this pattern, or this one, or this one. These all happen. This is not at all made up. Currently what we do is totally suboptimal, and it kind of hoists us on performance pretty regularly. We just copy it. So if you slice into an array, we copy all the data into a new array. you can imagine why that is not the best for performance. And then there's sort of this embarrassing situation where you're like, people are like, well, I wrote this code and it was really fast in NumPy, and why is it so slow? And we're like, well, you got to use this like view thing, and it's kind of awkward, and it's actually not as. You're just like, all right, I'm just gonna go. So we'd like to solve this problem. But how do you generate generic code? For the array case, you could do something. Essentially, what you want is for the number of dimensions of your thing, you want that many nested for loops. If you have that many nested for loops and you know the strides of each of the dimensions, you can generate really, really fast code to do this. That slide probably should have been right before the examples, but whatever, sorry. Okay, so what we're going to do is we're going to do this thing. We're going to use this generated function. So just to say, let's say A is rand, 3, 4. If we wanted to iterate through this with 2 for loops, the way we would do it is we would say for I1 equals, 1 through, we actually, size A, 1, and then for I2 equals 1 through size A, 2. And then let's say we just wanted to do print line, A of I1, I2 equals, and then we actually want to, print the element I1, I2. Yeah, we could do something like that. Okay, and that, that efficiently scans through and goes through all the things. And if you have a view that is strided or something, all you need to do is put an extra, you actually don't have to do anything special. You just, I1 starts at a different number and maybe steps by a certain amount with every loop. So it's actually super hard, super easy. Like doing it with linear indexing is crazy hard and involves mods and divs. Doing it with for loops is straightforward and fast. So what we would like to do is generate that code, but we have to generate that code for every possible number of dimensions of the array A. And this is where the staged function idea comes in. And so I'm just going to, rather than take you through writing it by hand, I'm actually just going to cut and paste the code. So this is an n loops example. And here's what it does. I'm going to just look at the code for briefly. So the way generated functions work is they actually look at they hook into the point in code generation where you're like, okay, I need a version of this specific to this type, and since the number of dimensions is part of the type, we generate different bodies for different implementations of this depending on that n. And you can see that in the type signature. So n loops is parameterized over t and n, where t is the element type, n is the number of dimensions. And then because of the @generated, this is what happens is this method body is actually not what runs when you run the code. It is what runs when you're actually deciding what to run. And it returns an expression which is then actually compiled and run. Bear with me here. I know that's a little confusing. During that, A is actually bound to the type rather than the actual value because you don't have the value yet. And so what this code does is vars is an array of symbols. Inner is this print line expression that we're trying to construct. Outer is initially the same as inner. And then what we do is we just go through for each of the dimensions that the array has. We say var is the symbol that is at that depth. We keep track of that var. Then we actually append some stuff to the inner print line expression. And then we actually redefine the outer expression. And that frowny face operator is our code quoting syntax, which we were actually just talking last night about changing. Then what you do is you say, I'm going to make this for loop. This is quoted code, and then I'm going to splice the previous value of outer into that. And so what you see is you build up more nested for loops as this goes through for each dimension. Okay. So I'm going to run this without the generated because we can actually see what it prints first. Oops, I ran it. All right, so I'm just going to delete the generated. And then we can have, so A is a two-dimensional root thing. And if we call n loops on A, it actually prints out the code that it generated. It returns it as a value, and we can print it, and it'll look normal. So you can see here that it generates pretty much exactly the hand code. It actually does one thing better. I had the loops in the wrong order. That is actually, this is the correct fast order to have them in, to scan through in column major order. Okay, that's fine, so we already had that code. Why is this exciting? Well, let's say that instead of A, it is rand 3, which is one-dimensional. Then we just get one loop. Rand 3, 4, 5, now we get 3 loops. 6, we get 4 loops, and 10. Okay, so we get lots and lots of nested loops. At some point, you might want to stop doing this because you should question why you need an array with that many dimensions. But people have done more bizarre code than this. So now let's actually do it. Let's actually define it with the @generated symbol at the bottom, at the top. And now it'll actually generate that code and then compile that and run it. And this is all transparent. Once you've defined this, you treat end loops as a black box. So A is still that. So end loops is A. And you see it goes through. This is actually exactly the same elements you would get from linear indexing. It's the same order, except it works for various things. So rand 2, 3, 4. It scans through that. And this is the fastest code you could possibly generate to iterate through all the values in a general array, even with strides.
So really what ends up being so magical about this, and really the good and kind of novel thing about it is how automatic it is. So when you do code generation, some of the big problems is really just kind of the logistics around it. Somebody has to be in charge of invoking the code generator, and then you get something back, and then you have to put that somewhere. It might be an extra source file on your disk, and maybe you need another build step, or you might have to keep it in memory and keep a pointer to it yourself and know when to call it. And there's extra sort of logistics and bookkeeping that goes around doing something like this. And in this case, we can automate that.
I believe OCaml, FFTW uses OCaml to generate C code. So yes. You can imagine what those make files look like, right? It's not a pretty thing.
Yeah, so in this case, basically, a library writer just puts @generated in front of something, and then they don't have to worry about when that's going to get called. Our compiler will call it as necessary, and then from the user's perspective, it just looks exactly like a normal function call API. They don't have to do a single thing different. They just call the function, and just internally, the method cache takes care of generating a special version and storing it where it needs to be, and then once it's cached in there, it can be reinvoked, whenever it's needed. So it's just very smooth experience.
Okay, and so we have.
Actually, we'll just go back to the prompt for 1 second.
Yeah, sure.
Yeah, so this end loops example is kind of motivating, but it's just to give you some flavor of how much more complicated this can get. So we have a.
I'll hold that for you.
Well, I'm not going to type very much.
Okay.
So we have a type in the standard library that people have implemented that does do an in-place non-copying view of an array. Which is this subarray type. And you can see if you look at it, there's lots and lots of stuff in there. So basically, these are basically the properties of one of these. So it has an element type, a number of dimensions, it has some underlying storage type, and then it has a tuple of indexes, which can be vectors, ranges, integers, or this special colon thing. So this has sort of a lot of information inside it. It's basically, there's a whole tuple of different kinds of indexes that it's using to view some array. And then once you have one of these, somebody might index this thing with some other tuple of indexes. And so at that point, this becomes kind of a difficult problem to generate efficient code for all these combinations of different kinds of views and different ways of indexing it. So this is one thing we use this feature for.
Adding generated functions to our language managed to reduce the size of the code for dealing with arrays in our standard library by just a massive amount. And it not only does that, but it allows us to solve problems that we didn't know how to solve before.
Let's see. I think is that it for the slides?
Yeah,
I think it is.
For the
okay.
slides.
So I have another example here that I really like. This example was made by Steve Johnson at MIT. This basically comes from E&M physics. So there's a technique, a numerical technique in E&M physics called the boundary element method, to be contrasted with the finite element method. The interesting thing about this problem, so this is a problem where the user inputs gives you some geometry and some potential functions, and they want to solve for, say, the potential everywhere. And the interesting thing about this particular problem is it's been very difficult to make a generic library for this problem, where you can just pass in anything and get the answer from the same library. And I guess the reason for that is apparently that when you do this problem, you get lots of integrals that are really difficult to do. You get difficult numerical integrals that have singularities in them, and figuring out the right, an efficient way to compute this integral is pretty difficult. So there aren't a lot of generic packages for this. So it turns out that you can use our system to make one of these. So all the details of the text isn't important. He made this really beautiful notebook, but the details aren't important. But basically what we do, so first he defines some types that describe the important properties of the functions that we're going to be working on. So this is an example of basically nominal function types. So Julia has started using nominal function types a fair amount. It's kind of like also what Java does with its lambdas. We are a dynamically typed language, so we feel like arrow types. Arrow types are great, but they do not work really that well for us in a dynamically typed context. So we haven't really come up with a satisfactory way to use them. So for now, we have nominal function types. But it turns out that nominal function types are actually surprisingly useful in lots of these kinds of numerical and scientific applications. And the reason is that people have some idea of what is the important property of these functions that I care about, right? They might not really want to care about or talk about the argument and return type of the function. They might not be thinking about that.
It's often just float to float. That's,
right.
And you're like, that's totally like doesn't help me at all.
Every function in the world is just float to float, or maybe two floats to one float if you're getting really fancy, right? So in this case, what they actually care about is basically the degree of the singularity. So he says, that's the key property. So you want a type that has that information in it. And so that's what this defines. So let's see. I'll just run that. So you can define the behaviors of some of these functions, and see now I can construct a first integral of a power law with certain parameters, and then just call it, and you get an answer. So this is kind of for a particular special case. So this was a special case that has an analytically known answer, so he could just write out exactly how it's supposed to work.
Can you explain what that is? Oh, so this call definition. So when you write f of x, that is actually an overloadable syntax. So you can define how something that is called like a function actually behaves. And the way you do it is you add a method to the call function, which is a generic function itself. And in this case, what you're saying is, when I see a call where the thing that is being called is of the type first integral with this power law p n business as its type parameters, and then x is a real argument, I would like to define that to be this. So this is defining that behavior, and that's what we're actually seeing here. We're defining f to be a particular first integral instance, and then we're calling it on the value 3.7. Does that make sense? I hope. Anyway.
So that was sort of a special case that you can kind of write by hand, like you can define any method of a generic function. But the general case is really, really hard in this situation. So he wrote some code to basically take a general one of these and figure out a Chebyshev polynomial that approximates the thing you need really well. But it actually wants to do that at compile time, because this process is way too slow to do at runtime, but you can, if you're a mathematician, you can figure out which part of it can be hoisted to compile time. And so, let me just evaluate this.
Those boxes are supposed to be subscript Ks, but apparently even on a Mac, you don't always get your Unicode right.
So here's the general version. You can see it uses this generated function thing, and the goal of this is basically to generate something based on the type of kernel function we have here.
Yeah, I would point out that, for example, it is doing an integral while figuring out what code to generate. This is like, we now have like a compiler step that is actually solving an integral numerically in order to then generate code that you're then going to run.
So here's an example of that working. So I just defined another one of these nominal functions, and all right, let's see. So we can just ask for what is the code generated for that. So here's the LLVM code. We can see there's actually an error check. If we just do a simple range check at the beginning, and then The rest of it is just a really nice straight line code of adds and multiplies with all the coefficients inlined. So you get basically, this is pretty much as fast as you can get for computing one of these approximating polynomials. And so you would just get all of these bits of code piling up in memory, and we're going to have addresses to them somewhere. And actually people will do things like they want to be able to have a lot of flexibility with these. They might make an array of these functions that has functions of various different types, and you can just call them and you effectively get a jump table to different routines of this flavor, sort of automatically when that happens. And this works like any other function. You can plot it if you want.
So PyPlot is a plotting library that actually, well, it's a Julia package that calls Python to do its plotting. We do actually have several rather nice native plotting libraries, but some people prefer PyPlot. Steve Johnson, who did the rest of this work, wrote the PyPlot package, so that is, I think, his preferred plotting package.
Yeah, Matplotlib has tons of plots, and it's really good, so just call that.
Yeah. And you can see this is mapping the first integral function over x over a certain range. And so you see that this is efficient enough to actually solve all of those and make a plot of it in fairly little time. How much time did that take? Let's see. Yeah, it's 55 milliseconds. That's sufficiently good. Anyway, yeah, I think
I think that's pretty much it.
So we're about done. Thank you. All right. And now, of course,
microphone.
questions.
Hold on, microphone.
This guy had a question.
How do you hash complex numbers?
How do we hash complex numbers? Well,
You didn't tell us.
why? Well, we could look at the code, I guess, but
I'm just curious now. Got me all worked up.
If I recall correctly, you just hash the components and then hash those together with some particular bit pattern.
yeah.
Okay. Thanks.
Yeah. The only thing you'd have to worry about there is you need to make sure that when you hash the complex part and it's 0, that you get. So you just have to XOR it with the zero, the hash of 0, to make sure that it cancels out and equals the purely real version. Yeah.
Hi, thanks for a very impressive demo. So from what I understand, you have at least two kinds of compile-time functions, the macros and then generating functions. So we've seen the benefits that generating functions bring to the table. So what's the point in macros then?
So yeah, what's the point of macros? Yeah, very good question. My thoughts exactly.
No. No.
But,
sometimes so macros essentially just operate on syntax, and so sometimes you don't like the syntax you'd have to write.
Yeah, I think the only real use of them is if people are just very fussy about their syntax and they just really want a very specific notation for something, and then that's the only way to do it. That's really the reason, I guess.
So you can see what the @time macro, that's a macro, and you can see what it does. It just sort of puts a bunch of stuff before and a bunch of stuff after, and then the expression you called in the middle. I don't want to have to write all that stuff myself. I also need to make sure that sleep doesn't get evaluated until after. If I sleep and then take the result of that, I'm not going to get very interesting times, right? So you do need macros for some things.
All right, we have more.
So,
okay, yeah.
First, I'm super happy to see that you integrated staging basically in a very nice way into the language, unlike OCaml and others that you have to build beforehand. But then I have a question here, because now it's so widely available. How do you manage the code caches? Because you generate a bunch of code basically for all these generated functions. So do you manage the code caches? How do you manage them? And what happens when people basically call, for example, these functions with very large numbers, so that you get megabytes of code, right?
So the question is, how do we manage the code cache, and what if people call these things with really big numbers or do sort of abusive things? Well, we just have to trust people, really. And the code cache right now, we don't do anything very fancy. It basically just keeps growing, and that has not really been a problem yet. But
we already generate a lot of code. Numerical computing is a good area for that sort of thing, because all of these, a lot of the techniques we're using here, JIT and macros don't generate that much code, but these ideas are old, right? They've been around since the 70s or the 80s, but people had these sort of small machines where how much code you generated really mattered. If you're working on a terabyte data set, you really do not care about 50 megabytes of code that you generated. So we haven't really hit that problem a lot. I mean, if we're trying to do stuff on embedded machines, it might be a different story, but that's not something we're doing just yet, but we are kind of thinking about it.
So this is a question regarding the first half of your talk. So I'm assuming you're familiar with Scheme, given your appreciation for macros, and thus you're probably familiar with the numeric tower there. So my first question is, do you have big nums and do you automatically promote to big nums? And if so, then what do you think about Scheme's division between exact and inexact versus your choice to automatically treat 1 and 1.0 as equal, even though they aren't referentially transparent?
You are probably a better person to answer this.
Yes,
our parser is actually written in Scheme, in a scheme that Jeff implemented. So
that was a lot of questions. All right, so we do not automatically promote to big num. That's an easy one. And also we have basically 2 forms of equality. So this is also, I think Common Lisp had about 5. Scheme has a couple. It depends how you count. We have basically 2. So there's the double equals, where 1 equals 1, but there's also a triple equals, and this is the disciplined kind of exact equality, the distinguishability based equality. So that for that they're not equal.
This is Henry Baker's egal.
Yeah. And so about the Scheme numeric tower, the Scheme numeric tower is really good. It certainly was very well designed. I think it's kind of a shame that it's difficult to implement in Scheme. You just have to use kind of big nests of if statements pretty much. I think it's sort of too bad that has to be kind of built into the language spec. What do I think of exact versus inexact?
It's also not extensible, right? You can't come and make your own type and fit it into the numeric hierarchy. So all of the Julia's numeric types are actually implemented in Julia. So I mean, even like int and float are just, we say here's a bag of bits, and here's how you add them, and here's how you multiply them, and all of that stuff is completely bootstrapped in the language. And if you have your own numeric type that you'd like to implement, it is in no way less privileged than the ones that we provide. We just happen to provide those to you. So I think that's a very big distinction.
Yeah, and the exact inexact I think it's kind of cool, but I suspect it's sort of not all that useful, because people who do numerical analysis don't really talk about that very much. So I think it's, at the end of the day, it might not actually be so important to have that.
In fact, there was one day where I decided that since rational is this exact thing, rational should sort of win in a lot of promotions. Like if you have a float and a rational, you should convert the float to the exact rational number that it represents and then give that rational. I don't think I've ever done anything quite so unpopular. Like, like I just snuck that in. This was a couple years ago, and like there was, people were screaming bloody murder, and we reverted that very quickly. Because it basically means that rationals, so exact types poison inexact types in that way.
So has Julia had any adoption outside the scientific community? Are people making websites with it, or games, or graphics, or anything like that?
There's a little bit of interest in I've seen, so there's one guy who made a really impressive Quake engine in Julia using OpenGL, but I don't think anybody's using that in earnest. It was just a cool project. There's another guy at MIT who's doing sound stuff. So he likes the same things, that the numerical people like about it, is because, you can write simple code and get really fast implementations of it. What he doesn't like is that our GC is not real time. So, scientists don't really care about big pauses in GC because it's all about throughput. If you're generating live music, then you really do care about a perceptible pause in GC.
But yeah, I think the basic answer is yes. I mean, I don't think people, least of all us, really want a super niche programming language anymore. So, I think if you look at it, it's very clear that it's a really general purpose language, and people are starting to use it for other things.
Yeah.
I'd like to first off say that. So I work on Idris, and one of the things people love about it, I think, is that we have really pretty colors in the output, and that was inspired by a Julia demo I saw a couple years ago. So
great, thank you.
Thanks for helping improve our language.
Yeah.
But in light of the keynote we had this morning about sort of live environments that are better than just a REPL, what are your plans for Julia along those lines, or are there plans to
Well,
sort of do something nicer than just an IPython notebook?
Oh, nicer than an IPython notebook? Are you kidding me? I mean, what?
For example, with the debugger.
Well, I would put a debugger in the IPython notebook.
Yeah, no, I mean, there's been some more. There's a project called Juno, which is a light table with lots of Julia goodies baked into it. Some people really like that. I'm kind of old school. Like, I like a text editor and a REPL. But this is like the fanciest REPL I've ever used. It's got a lot of interesting features. I mean, I'm sure you noticed that, like, you know, you can do multi-line editing. You can go up and like change things, and you know it's all pretty straightforward to use. It's not that straightforward to implement. You can also shell out, so you can say, you know, ls. And you can see the different things. There's also a help mode where you can say, you know, I'd like to know what you know, help. Meta help. Yeah, so, but I think at some point we will want to develop something that is like, more like, you know, what I'd love to see is something that is, you know, could replace MATLAB for people who use MATLAB and like that style of thing, but could also make, you know, me and Jeff happy, right? Like I use Sublime Text, Jeff uses Emacs, and you know, MATLAB kind of sucks. It's the IDE like gets the job done, but it's really painful to use when you go back to it after this kind of multi-line. You can't do multi-line editing in an IDE. I don't get it. Yeah, so we'd love to have something that covers all of that.
I mean, I'd love to reuse more stuff too. I mean, like reusing IPython notebook has been very successful, and you know, whatever people do in that area, I hope we can, you know, we can take advantage of it.
Yeah.
Yeah, I have two questions, but first a quick bounce on the macro question. I think the true power of macros, especially Lisp macros, which work on the AST, is actually proper compile time metaprogramming, which is also a very important thing.
What? Proper compile time?
Proper compile time metaprogramming. That's the true power of Lisp macros.
Well, what do you mean by proper?
Proper, I mean working on the AST.
Yeah, ours work on the AST too. That's like.
Yeah, I know.
Yeah.
That was a bounce on the
Right.
previous question.
Okay.
So the two questions I have is, so Julia is obviously stuffed with features inspired probably from Common Lisp and probably also from Dylan. I'm not sure about that one. And you said, I heard you loud and clear, that you like Lisp. So the obvious question, I guess, is did we really need yet another brand new language? Why not building on something that's been around for a long time and which, you know, has a strong and long-lasting community? Why the need for something completely, started from scratch? That's the first question. And the second question is really a technical detail. Last time I checked, I think Julia didn't make any difference between binding and assignment. So the question is that still the case? Or am I wrong, am I right? And if that is actually the case, then what the hell were you thinking? Thank you very much.
I mean, we could have done something like compiling to Common Lisp. You know, there are a lot of really, really excellent Common Lisp, so that, you know, that might have worked well. I think, probably the difficulty would have been that, you know, there would have been a lot of tension about how much like Lisp it's supposed to work, for example. And you know, we didn't want to be saddled with that. And I think there are just certain specific places in the design, particularly the type system, where you really need to be able to basically force something on people. And you know, people really need to go along with that. And you know, just having picked the appropriate minimal amount of thing that you're really going to force on people, then from after that point there can be lots of flexibility. So I think to be able to freely experiment with the type system without people complaining too much about interoperating with a host language, I think is probably, you know, necessitated doing this differently.
Also, so Julia has we didn't talk much about multiple dispatch in that, but we've really broken ground in terms of what you can express with multiple dispatch. So Dylan does have it, Common Lisp has it, you can do multi-methods in Clojure. But I don't think, Dylan is probably the closest in terms of having really good performance with that, and also having them be the default. But in Common Lisp, you have to say, you know, def multi, right? You can't just, or def generic and then def multi. You don't, like, plus or just built-in functions by default are not generic functions. In Julia, everything you see that you call as a function is a generic function, which means everything is also extensible. And another flip side of that is making everything fast despite that. So like we define all our entire standard library, like for loops and like iterating over using integers, that's all defined in the language in terms of operations that are defined in terms of generic functions. And I don't know if anybody else has pushed the performance of generic functions that far. And that's actually addresses why we don't automatically promote to big ints, right? So if you're relying on an implementation language as integers to be efficient for implementing loops and whatever else, then it's fine to have a little bit of overhead. But if you're implementing all of that stuff in the language itself, then you really can't afford to have that overhead.
All right, and then on binding versus assignment, I think I would just say that what we have, I think, is just very convenient and unsurprising to people. I think it just tends to sort of do what they expect by default. I don't know. I mean, nothing has blown up so far. I mean,
it's pretty close.
I still have all my limbs. I think it's all right.
It's pretty close to what Python does as well, which people seem to be okay with.
Yes, yeah, it's very close to that. Yeah. So it might even be identical, actually. I'd have to look at the details. But yeah, I mean, I would look at, if you're able to find an example that really does something bad, please send it to me. I'd be curious to see.
In general, if you introduce a typo in your code, then it's going to go to pages, and these kind of errors are usually very hard to debug. That's essentially it.
Yeah, that may be, yeah.
Most dynamic languages have this issue.
Okay, I think we have to wrap up. We're a little bit over time. Let's thank our keynote speakers. It was a very nice demo, nice talk. Thank you.